again. And I have a couple of quick announcements before I introduce Ron. So upcoming, and maybe Rini, you can specify more of what these things are. So Noah Feinstein is coming on March 18th.
Next, so Wednesday, right?
Next, yeah?
Next Wednesday, right?
Is it? No.
No,
2 weeks.
two
No,
Wednesdays.
spring break.
Oh, spring, so we don't have anything.
Right, and
And
then
the
Noah
next week
Feinstein
is
is
Noah
coming.
Feinstein
And
for-
is he doing a talk? What is he doing?
Yeah, talk, I don't know, but it'll come out on our
Tap
weekly
dance.
emails, so check
I bet he
where and
would.
when. But if anybody wants to get on his schedule, please
Yep.
message Zach, our coordinator back here, and he'll
I
put
do.
you on his schedule, meet separately.
Awesome.
I'll just say a couple things. There's a lunch for graduate students from 1 to 2, and 1 to 2:30, I don't know. Oh, 1 to 2, and then his talk is at 2:30 instead of the regular time. And then he pretty much only has time from like 5:30 to 7:15. So if you're interested in meeting with him, please let me or Andy or Zach know
Cool.
soon.
Thank you.
Then we have two jokers giving something on March 25th. That's Danny Caballero and I. So you can come to that. That will be interesting. That's about, we'll talk about the physics class that we did and looking at some data from that. And then on March 27th, which is a Friday, there's going to be a co-integrate math talk. Do you know who the speaker is? I know, but they're always fascinating.
No, I don't know, and that one's in the afternoon though,
Okay.
and we have pie in honor of him.
Oh, my daughter is celebrating Pi Day because this is a big year for Pi Day because it's 3.1415926.
That's right.
It all, you can do it at 9:26 in the morning. Did you know that?
Wow.
Wow.
That's right.
He has a moment of silence.
So her school is doing, McDonald Middle School, she goes, is doing Pi Day on Saturday at 9:26 in the morning. It's a big thing. That makes no transition at all into Ron, but we'll do it.
I like pie.
Yeah, all right.
That's
Ron
fine.
likes pie. And there's Ron Gray. He's an assistant professor of science education in the Center for Science Teaching and Learning at Northern Arizona University. And we get along because we share a lot of things that we think about. So one is secondary science teacher preparation, another one is ambitious teaching, and as you know, Ron is sort of the third person in the series of people that are interested in science studies and education. So thinking about why science is the way it is and what that means for education. So in addition to all of his fascinating things that he does in science teacher preparation, he's also a world traveler. He's done work with the Cheetah Conservation Fund. And have you been to Namibia?
Yeah, about 5 or 6 times. It's a beautiful place.
And then apparently Borneo and Malaysia. Do you go to Borneo, Malaysia?
Yeah, I was supposed to go this summer and it got
All right.
messed up.
So you
Grants.
can talk with travel
Messed
in
me
the
up.
world and Costa Rica, which is a nice place to go. He did his PhD from Oregon State University, and before that he was a science teacher, like I was too, and he's done lots of little fascinating things. So we have lots to talk about. And we'll turn it over, and at about 12:55 he'll call it a day, and we can have time for questions. So thanks, Ron.
Perfect, thank you. And thank you very much for the invitation. I'm very happy to be here. This is my first time in Michigan. And I'm in Flagstaff, which is very cold, 7,000 feet, and I left with snow and cold, and I got to snow and cold, so I need to fire my travel agent or something. I'm not sure what's going on. So my goal today is just to present some ideas and get some feedback on those ideas as to ways in which we can utilize the science studies literature to help us flesh out our work with science teachers. That's kind of the goal. But as David was saying, the series is about science studies, so I threw in a couple slides before we get going on that, just to kind of talk about some of the things that I've been thinking about a little bit more in terms of science studies. So one is this shift, which is finally starting to happen, is where a lot of the work and people in science education are starting to move past just philosophy and history of science. Philosophy and history of science are important, and most of what I'm going to talk about today actually stems from philosophers of science. But other fields in terms of sociology of science, anthropology of science, economic, you name it, there are a number of other fields that are making very strong contributions, and I think it's important to kind of make note of that. There are still a lot of people who very much focus on philosophy and history of science. Actually, there was an NSF-funded conference at Boston University a couple of years ago that was specifically only about philosophy and history of science. And so I guess the way I feel about it is there's a lot of richness outside of those fields as well that interact very well with those fields that we can focus on. I think there's an importance as we look into science education, there's an importance of the role of a mediator, and that is people like me and many of you in this room who delve into the science studies literature, but also start to think about how it translates and what the purpose of that translation is into science education. It's not a direct translation by any stretch, right? Part of what we'll talk about today in philosophy of science, the philosophers go far deeper and have their disagreements, but at a level that as the mediator, I can say that that's a level that's perhaps not relevant for the work that we're doing. And so that mediator role is, I think, very important. And often when we look at science studies literature, especially history of science, but we tend to think about it in terms of it provides context for what we're doing, thinking about it in a classroom, from the classroom side of things. It provides context, but I think there are some other roles that it can play, and so maybe that's a discussion that we can have here at the end. And then this other idea of kind of micro versus macro, and you know, in science education, a lot of this is under this moniker of nature of science, which I think is at a place right now, this nature of science idea is at a place right now that there's a lot of very fruitful areas to expand. And macro, by micro, what I mean is kind of lab bench, field-based, how do we do what we do, and macro, these larger things about how the community of science works. And so I think the practices, the shift toward practices and that the way they've been put together in the next generation science standards have done a nice job of kind of framing micro, but I think there's some really interesting work to happen to frame macro again. And so I kind of come at it from that. I also have been playing with these ideas quite a bit, and that I teach a graduate level nature of science course. And we've been playing with it a bit. So there are a number of consensus lists as to what nature of science is, and in my courses I've tried to push back on that and instead get them to create their own list, get them to create their own ideas about what it is that we can draw from these literatures from the science studies communities that would be relevant to them in their context. So the course is kind of redesigned, and the first basically half of it is looking at primary and secondary sources from philosophy, history, sociology, anthropology, a number of different types of fields of science, and also quite a bit from the scientists themselves, because there are certainly some scientists that have done some wonderful writing about the nature of their work. And so we spend a lot of time looking at all these, discussing it, debating it, and to where that line hits is where they write a paper where they put their foot down and say, here are some things that I believe, and here's my evidence for it, that this is relevant to my 10th grade chemistry class, or my 6th grade integrated science class, or whatever it might be. So that's been kind of it. Then the second half of the course is really about giving them the tools to think about how that relates to the classroom in ways that are useful. So this is a kind of, in terms of science studies, this is what I've been thinking about a lot lately and been trying to play with within this course, and I think it's been a useful endeavor so far. So on the topic that I'm supposed to be talking about, science, I would make the contention that we tend to, at times, and there's good reasons for this, but we tend to overgeneralize about the things that make science science. In reality, we know that there's an incredible amount of diversity within the disciplines of science, and these different disciplines actually have different expectations. They have different ideas about what counts as evidence. They have different ways of doing explanations and arguments. All these different things, and this is what the science studies community does a really nice job of going into in detail. But there's a medium ground. There's a space in between everything revolves around the word science to looking at the detail of these fields and subfields. And that's part of what the talk is about today, is to try to find, is there a way that we can get a bit more in depth, flesh out the ideas, the ideas of methodologies and other concepts within these fields without going into the depth of knowing, having a PhD in each of these fields, right? There's somewhere in between that I think we need to land in science education, and I think that would be a useful thing. So the problem as I'm thinking about it is that the development of our classroom inquiry experiences, it requires an understanding of how scientists actually do their work. And science studies is a place in which we can start to look at that. These experiences that we give students in our classes are only approximations of what scientists do, and they provide an image of science for students and for the public at large as they move forward. And so that's why focusing on the types of experiences kids have is important. The decisions that we make about these specific experiences impact the way they view science as a whole and the relationship between the different fields and disciplines of science. And in the past, science educators have primarily focused on an image of science taken from physics, experimentation, replication. And we could say that has left out a number of different fields that don't necessarily work in the same way, but are just as legitimate. But it implies that they are less legitimate because of this image that we're rather implicitly giving based on what we choose to do in the classroom. So I think there are a couple of impacts we can think about to this kind of misunderstanding of the incredible variety of ways in which we undergo science across the fields. There are a couple of things that I think are specific impacts we can point to now. One is in geology. Jeff Doddick has written nicely about historically that geology has been really thought of as a derivative of physics that could be reduced to physics. And so starting with post-Sputnik, geology has definitely declined in school curricula. So K-12 students have very little access to the earth sciences in most states. That's starting to change. Texas, New York, other states are starting to put high school level earth sciences class in, especially because of climate change and earth system science. But for many of us, I know the last time I had geosciences before college was middle school. So we had very limited engagement in geology for students, and this affects the way students understand other subjects like climate change and other things. They don't have those intellectual resources to draw upon to necessarily understand this, and this is, I think, one of the reasons we have climate change denial and all these other things that are happening right now. And then obviously in evolution. Jim Stewart has written very nicely about this. This is one topic that's been singled out specifically as being unscientific because it can't be justified experimentally. And let me show you an example of that. I don't agree with that statement, by the way. But that's the idea. This is from the, what do they call it? The Ham on Nye debate, right? So Bill Nye, the science guy, debated about 2 years ago or so, debated Ken Ham from the Answers in Genesis group, which is a leading creationist group. And in the very beginning of the debate, they gave them each a few minutes to lay out their argument before the debate really started. And what I want to play for you is just a couple of minutes of Ken Ham's response. Okay? And then we'll chat about it. If I can hit the button.
Just this opening statement, I want to concentrate on dealing with the word science. I believe the word science has been hijacked by secularists. Now, what is science? Well, the origin of the word comes from the classical Latin scientia, which means to know. And if you look up a dictionary, it'll say science means state of knowing, knowledge. But there's different types of knowledge, and I believe this is where the confusion lies. There's experimental observational science, as we call it. That's using the scientific method, observation, measurement, experiment, testing. That's what produces our technology, computers, spacecraft, jet planes, smoke detectors, looking at DNA, antibiotics, medicines and vaccines. You see, all scientists, whether creationists or evolutionists, actually have the same observational or experimental science. And it doesn't matter whether you're a creationist or an evolutionist, you can be a great scientist. For instance, here's an atheist who is a great scientist, Craig Venter, one of the first researchers to sequence the human genome. Or Dr. Raymond Damadian. He is a man who invented the MRI scanner and revolutionized medicine. He's a biblical creationist. But I want us to also understand molecules to man evolution belief has nothing to do with developing technology. You see, when we're talking about origins, we're talking about the past. We're talking about our origin. We weren't there. You can't observe that, whether it's molecules to man evolution or whether it's a creation account. When you're talking about the past, we'd like to call that origins or historical science, knowledge concerning the past. Here at the Creation Museum, we make no apology about the fact that our origins or historical science actually is based upon the biblical account of origins. Now, when you research science textbooks being used in public schools, what we found is this. By and large, their origins or historical science is based upon man's ideas about the past, for instance, the ideas of Darwin. And our research has found that public school textbooks are using the same word science for observational science and historical science. They arbitrarily define science as naturalism and outlaw the supernatural. They present molecules to man evolution as fact. They are imposing, I believe, the religion of naturalism or atheism on generations of students. You see, I assert that the word science has been hijacked by secularists in teaching evolution to force the religion of naturalism on generations of kids. Secular evolutionists teach that all life developed by natural processes from some primordial form, that man is just an evolved animal, which has great bearing on how we view life and death. For instance, as Bill states,
it's very hard to accept for many of us, that when you die, it's over.
But you see, the Bible gives a totally different account of origins, of who we are, where we came from, the meaning of life, and our future. That through one man, sin entered the world, and death through sin, but that God so loved the world that he gave his only begotten Son, whoever believes in him should not perish and have everlasting life. So, is creation a viable model of origins in today's modern scientific era? I say the creation-evolution debate is a conflict between two philosophical worldviews based on two different accounts of origins or science beliefs, and creation is the only viable model of historical science confirmed by observational science in today's modern scientific era.
So that's my talk. So what do you see out of it? What types of ideas about science does he have? He has a very good reason for having those ideas because it pushes another agenda forward, but what are some of the ideas that he's putting forth that are somewhat problematic? What do you see? Yeah, please.
Well, the arbitrary distinction of what he calls the historical sciences versus the experimental sciences.
So what's his...
As though there were some different methods being applied to these two areas.
So what is what's his reason? Outside of he has the reason because of the religious aspect of this, but he has what's his argument for why those two things are separated?
Like his argument that I don't agree with?
Yeah, his argument.
One is about what's happened in the past versus what's happening now.
Perfect. Did you? Yeah.
Yeah, I was just going to say that, and like he's basically missing the role of inference in science. For him, there doesn't seem to be any role of inference. It's just observation or experiment equals fact.
Right. And so it's interesting, if you go back to this debate and watch the very beginning, they introduce him, and he has a degree in science. He was a biology teacher before he went into a very different profession after that. So he uses those as his credentials as he's coming into this. But so he's putting a number of things forward. But the most important one for today is he's putting forward the idea that if you weren't there, you can't know. Right? If you weren't there, you can't know. And so anything that happened in the past that a human was not there to experiment on or observe, we can't know about it. And if you go to the Creation Museum, which is, I would really like to go. If anyone wants to, has anyone been?
No, my kids have.
I have friends who have been.
Oh, I want to go so badly. But one of the things you said, that's kind of the theme that goes through it, is that you can't know what happened in the past. There was only one person there, God, and so that's the only account that makes sense. And he thinks of this as a scientific argument, right? So these are problems. I would call these problems. And I think what we're talking about today is this focus on experimentation only in schools. The way that science in the making, we only give images of experimental science, can lead to a host of problems within geology, within evolutionary biology, within climate science, and a number of other places. So the purpose of today is to use this construct this is actually from Philosophy of Science, of experimental and historical sciences, to provide teachers and students a richer image of what authentic scientific practice looks like. And then I'm going to examine the scientific practices as described in the framework from the perspective of the historical sciences, just to see how well it matches up. And then at the end, to provide some expanded language that I think is necessary or useful to start putting into the discussion here that would help out in the classroom in this regard. So, providing a reasonably authentic context for science teaching requires understanding of what actually happens in the sciences, obviously. Where can you find this? Well, ethnographic studies like Latour and others, and also from cognitive scientists like Guerre, Nersessian, they've studied this in a variety of sciences. However, with very few exceptions, the vast majority of these studies have been in experimental sciences like physics and chemistry. And so there are very few examples of historical, or even just in a more general sense, non-historical sciences. So there's not a lot to draw upon from these certain science studies literature that are out there. The one example that I pull out there, Latour, 1999, that's Pandora's Hope. One of my favorite books, if you haven't read, that's just fantastic. But in the first chapter he sets it up, and in the second chapter he follows a group of soil scientists down to the Brazilian Amazon to answer the question, at this spot is the rainforest receding or pushing forward? That's, I think, as close as we get from this group of researchers to give us some background understanding of these things. So because of this concentration on experimental sciences leads to a mistaken impression that the disciplines in general operate in a similar way and that their methodologies, in terms of their methodologies and reasonings employed. The lack of focus on historical sciences, which I'll define very clearly here in a moment, like paleontology, cosmetology, evolutionary biology. Where do we draw from? And I would say that the people who have been working on this is a group of philosophers of science, including, most importantly, Carol Cleland at CU Denver? Boulder, one of those two. And others, and also the scientists themselves. Stephen Jay Gould has written prolifically, he writes prolifically about everything, but wrote prolifically about everything, but has written prolifically about the ideas around historical sciences. Jared Diamond, in one of my all-time favorite books, Guns, Germs, and Steel, is definitely making a historical argument in that book, and at the very end spends a number of pages talking about why he thinks that his conjectures are real and historical science, how they work. Ernst Mayr wrote about it in '85, so there are a number of sources that we can draw upon as we move forward. Hello. Not a problem. Say hi for me. So this distinction between experimental and historical sciences is largely based on epistemological differences from which methodological differences have arisen, and I think understanding that is the crux of all this. But all scientists don't agree with this. Ernst Rutherford famously said, "Science is either physics or stamp collecting." Probably not too interested in hearing my talk today. Lord Kelvin, William Thomson said, nothing is science if it cannot be quantified." It's not a horrible statement, but there are some areas in science where quantification is not necessarily possible or useful. So even Louis Alvarez, who won the Nobel Prize in Physics, but also was a co-author with his son about the KT boundary asteroid hypothesis, disparaged fields like paleontology for not doing, quote, real science. And I couldn't find a date on that. I don't know if that's after the paper with his son or before. We'll see. But my favorite and the most modern is Henry Gee, or G, I'm not sure how to pronounce his name, who is still a senior editor at Nature, a very powerful person in the field of science, said that historical sciences are subjective, as they can never be tested by experiment, and so they are unscientific. They rely for their currency not on scientific tests, but on assertion and the authority of their presentation. That was in a book from 1999, I believe it's called Deep Time. The whole book is basically about that, about how most large chunks of science shouldn't be considered science because they're not experimental in nature. It's a pretty fascinating read. Senior editor at Nature. See, that would be problematic. So in philosopher science, the philosophers have taken on these critiques, and quite well. Carol Cleland, as I said, is the person who really started this debate and has played a large role within it. And she has said that historical sciences have evolved methodologies to cope with what philosophers call the overdetermination of past events, whereas experimental sciences have similarly evolved other methodologies to cope with underdetermination of future events. And what she means by that is all types of science have problems, right? And methodologies evolve out of trying to deal with those problems. And she would make the case, and others don't necessarily agree with her wholly. I don't know exactly where I stand on it, but she would make the case that means they are just as legitimate in terms of kind of their kind of epistemic power as each other, which has been quite interesting. So others have tackled this. Brown, Curie just came out with 3 papers. One of them is wonderful if you like this kind of thing, where he actually goes into the paleontology literature about the marsupial lion, a fossil found in Australia, and goes into extreme depth about all of the different studies to understand the physiology and ecology of this lion, in quotes. It's really more of a big koala bear with teeth, but and uses that to talk about the role of historical science. It's a really nice paper. Peter Casso, who's at my institution, Tucker and Turner. So there's a number of people, and you can see by the dates that this is something that's been going on for a little while and is still extremely active. So let me define the two, and then we'll go into more detail. So the way that Cleland and others define it is that experimental sciences are those that ask questions in which direct experimentation is possible. Therefore, knowledge is constructed through controlled experiments in which natural phenomena are manipulated, often in order to test a single hypothesis, like in much of chemistry, physics, molecular biology, geophysics. as opposed to historical sciences in which scientists gather evidence by observation because direct experimentation is usually impossible. These sciences often utilize observational evidence in order to investigate ultimate causes about past events whose effects must be interpreted from complex causal chain of events like paleontology, cosmology, evolutionary biology. And I think we can put together,
Can you go back to slides?
Yeah.
Both of those involve the phrase direct experimentation. Can you give me a
one says it's possible and the second one says it's impossible.
well, what does it mean to have direct experimentation?
So what I use, experimentation is a word that's kind of like inquiry. It can be used very large and very small. I'm using it small, so I'm defining it as manipulation of nature, as opposed to collecting evidence in which you put those pieces of evidence. And I have a slide here in just a moment about that, but direct manipulation of nature. Yeah.
So where in that context would, for example, medical research fall? Where you're
Right.
not able to isolate variables
Right.
because of a whole variety of factors, but you're also not in the historical science context.
Right.
Is that a third form? Are we?
Can you wait a couple slides?
Okay.
I promise I'll get there. So there's two, in terms of these two types of sciences, this is, I think, a framework that's useful in distinguishing between the two. Maybe this helps in terms of some of the questions. I think there are 4 distinctions that you can use to distinguish between the two. One is the epistemic goal, the nature of the objects under study, the method of evidence construction, and the quality standards across those. So let's look at these 2 different modes, types, as it were, and then I'm going to give you a big qualifier after this part. So with the 4 different areas in the framework down below, experimental sciences, in terms of their epistemic goal, is to find general laws or statements of natural phenomenon. In terms of what they study, the phenomena under study, they tend to be uniform and interchangeable entities. One electron is like every other electron, right? Method of evidence construction, manipulation of natural phenomena, thus experimentation, to often test a single phenomenon. The quality standard tends to be effective prediction, so measuring data and against your original predictions based on evidence. So physics, chemistry, molecular biology, those. Compare that to historical sciences, where the epistemic goal is largely to find causes of past phenomenon from present traces of evidence. In terms of the nature of the phenomena under study, they're complex and unique entities. The dinosaurs only were knocked out once, right? So they tend to be very unique events that are happening. And there are some that are trying to look across, say, mass extinctions and find patterns within that. But for most of the work, they're about very unique things that happen. The method of construction tend to be observation of natural phenomenon, often to test multiple competing hypotheses against each other. And that we tend to measure the quality by effective explanation as opposed to predictions, because predictions are quite tricky in the past. So evolutionary biology, cosmology, paleontology. So a quick note on what you're asking. So it's important to note that what I'm definitely not saying is historical sciences don't do experiments, right? That's not useful. So or the other way, that experiments don't do other things. So experiments have been conducted in genetics and biochemistry that are obviously instrumental in evolutionary biology. Radiometric dating, grounded in statistical law of quantum mechanics, is essential to a vast array of historical sciences. But to quote Jeffries, in historical sciences, experiments are more of a means to an end as opposed to the end itself. So they obviously do a number of experiments, but it's the last part that the experiments can't do for them. So a note on kind of dichotomies. What I don't want you to leave with is me thinking that I said that these are 2 distinct groups and that we should move forward with these as necessarily 2 concrete groups. I think there's a substantial amount of overlap. So you can think about it in the Venn diagram way, or Cleland talked about it as a continuum from more experimental to more historical, and then a mix of things in the middle. I also like kind of this idea, and taking the quote from Tucker, that the distinction between historical and experimental sciences runs through rather than between disciplines, right? So this is a way of really kind of thinking about methods, not disciplines themselves. So if we look at those across, I think you can talk about experimental sciences going all the way across those. right? This is about the questions that are being asked and the methods being used, not which discipline you're in. I couldn't come up with a good example for chemistry. If you can think of a good historical chemistry example, I'll take it, and I can move my little bar to the left, which would make me very happy. But as it stands, in terms of cosmology, evolutionary biology, there are a number of ones in earth sciences. I think this is a better way of thinking about this. These aren't hard, fast categories. What the goal of this is to finally use this as a heuristic for teachers to think about the different ways in which inquiry can be thought of in the classroom. We've already used historical sciences a bit in science education research. In the earth sciences, Kip Alt, Phil Siak-O, Jeff Doddick, and others have written quite a bit about this. If you've never read Kip Alt's work, it's really fascinating. He's an earth science educator. He just came out with one very recently on the Cascadia subduction zone and the way in which we have come to understand the role of the subduction and earthquakes in the Pacific Northwest. It's a really beautiful paper. In evolutionary biology, as I mentioned before, Jim Stewart has written quite a bit about that. In 2009, Doddick and colleagues put together an interesting study in which they went and looked at, I think, 1,600 scientific journal articles and did a content analysis run through a computer. So the other two are computer scientists. Looking at journals, top-rated journals and journal articles from across a wide array of sciences. And we're able to show that the way in which the arguments were constructed across those papers was different between the two. It was kind of an interesting little paper. A couple of years ago, I worked with a colleague, and we looked at this with classrooms, and we looked at the same teachers teaching two different types of units. One historically based, like evolutionary biology or formation of the solar system. The other experimentally based. What was it? Genetic or molecular biology and I forget what the last one was, and then looked at the patterns of their arguments across those and were able to show very distinct differences in the way they were arguing for presenting the information within those units. So it was all very implicit. They would not say they did it differently. In fact, they explicitly did not say that they did it differently. But the seeds of those differences were there, which was very interesting. And curriculum has been put together. There's a book through NSTA Press, Adventures in Paleontology, that gives some nice examples of this type of work. So I think as we move forward and think about bringing this idea of historical sciences in, we need some additions to the language of inquiry. So if you follow Lemke, as I do, in saying that language is a system of resources for making meaning, then the language that we use needs to fit what we are doing. Right now, the language of classroom inquiry is very much about experiments, controls, variables, predictions, hypotheses. These are the vocab in Chapter 1 of the science textbooks in K through 12. But I think there are a few other ideas that we should add to this, including retrodiction, abduction, reasoning from analogy, and multiple working hypotheses. So retrodiction is the opposite of prediction, an inference about past events. So for example, Alvarez and the group tested the asteroid hypothesis by searching for impact debris, glass, shock waves, a number of different traces that would support their idea. So if this is true, then I should go back and be able to find these is a retrodiction, or postdiction is the other way you find it written sometimes. Abduction is the third category after induction and deduction. Abduction is a type of inference in which an explanatory hypothesis is generated. So starting kind of the reverse of what we normally think of. So an example, Darwin presented his extended argument in Origin of the Species for natural selection as the best hypothesis for explaining the available evidence, the idea of best hypothesis. And there are a number of people who have done some really interesting work looking at abduction with kids and the process of reasoning through abduction with kids. We also, often in historical sciences, reason through analogy. So utilizing present causes to explain similar events in the past, and the principle of uniformity helps us do this. For example, the reconstruction of the locomotion and behavior of extinct animals is often based on the similarities with extant animals. In the marsupial lion example, they went to lions and koalas and everything they could find in the intermediate to take measurements and to try to use them as analogies for this creature. And then last is the idea of multiple working hypotheses, which has been around since the mid-1800s in T.C. Chamberlain, one of the original American paleontologists. So this is the process by which we have multiple possible hypotheses that are generated early in the work and systematically compared against the evidence. That means sometimes they can be knocked out and one ends up being the winner, or it can mean that they end up being shifted through and combined as the evidence necessitates. So for example, hypotheses to explain the extinction of the dinosaurs included random chance, magnetic reversal, a nearby supernova, volcanic activity. If you read the original Alvarez paper, throughout it, they are constantly bringing up these alternative hypotheses and talking about the way in which their data supports their hypothesis as opposed to those. So I think these are some language that can help us as we move forward and thinking about diversifying the experiences kids have away from purely experimental sciences. So we have made recently this shift toward practices, and with the next generation science standards, we now have these 8 practices, and this has been obviously a major step forward. So what I want to do now that you kind of have that framework in your head, is to go back and look at the standards and see how this distinction relates as we move forward. So as we examine the framework, first off, they are, without question, the practices, not the entire framework. The practices are general enough to encompass inquiry across all this continuum of sciences without any problem. And in fact, the authors state that they are written in ways as to, quote, not overemphasize experimental investigation at the expense of other practices, which is fantastic. However, in the descriptions of the practices within the framework, they definitely prioritize experimental over historical sciences. And let me give you some examples. So there's the practices on the left. If you go through the chapter on practices, which is very well done, I'm not knocking it, I am on board, I love it. But if you go through and look, if you look at 1 through 5, which I think we could categorize as the kind of the methods piece, the more micro piece. The examples are, every single one is from an experimental sciences: particle theory, ideal gas laws, atomic theory, gravitational forces, electromagnetic waves. It's not until you get to 6, constructing explanations, that we see any examples of historical sciences. And the examples given are Big Bang and Darwin's theory of evolution. What does this mean? I think what it means is that we tend to value the end products of historical sciences and less the methods of historical sciences. We obviously talk about Big Bang. We obviously talk about Darwin. We obviously talk about continental drift and plate tectonics. These are very important topics within the curriculum in K through 12, but there's less of a focus on how we know what we know in those fields as opposed to in terms of experimental sciences. And far more importantly, there's far less inquiry activities that students are engaged in experimental versus historical. So I think that's an important point to make. So as we go back and try to flesh that out a little bit more, so we know that the epistemological and methodological differences between these reveal small but very significant differences in the way these practices might be enacted. So now looking at this very much as a teacher-educator, science teacher-educator, how can I help my students understand what these practices are in general terms, but also what are some of those fluctuations in the way they're used and applied across disciplines, I think is the level. As originally where I talked about science versus a complex understanding of all the sub-disciplines of science, we want to be somewhere in here, right? And I think this is where we kind of plant our flag. So if we look at, I'll turn your head at once. If we look at the scientific practices across, we can play with some of these just to see some of the differences between them as we go forward. In terms of asking questions, historical sciences ask questions about very unique entities or events that can't be manipulated experimentally, such as what caused the Permian extinction. Whereas in experimental sciences, they ask questions about uniform entities for which experimentation is possible. Questions like, what is the structure of DNA? So they ask somewhat different questions, and those questions are vital because those questions are what lead to these differences methodologically down the line. I skipped over developing and using models because I'm not quite sure exactly what the difference is between those. I haven't had a chance to look into that as much. Planning and carrying out investigations. In historical sciences, they're largely observational, as we talked about, utilizing retrodictions, abductive reasonings, and some of these other concepts. And in experimental sciences, largely experimental manipulation of these. So in terms of planning out the investigation, they're planned out differently. There's a nice paper by Curie that I talked about before, called it, he said, historical scientists are methodological omnivores. in which there are less standardized techniques and more creativity in the way that investigations are put together and the way that we analyze things are important. In terms of analyzing and interpreting data, in historical sciences we have evidence is utilized to evaluate multiple hypotheses in order to narrow down or combine into the most likely explanation. In experimental, we compare to predictions, right, and use that comparison as our quality of moving forward and how to make arguments based on that. In terms of constructing explanations, in historical they're most often narrative form, and most often only relevant to the unique phenomenon that is under study, right? Trying to draw across those cases is quite difficult. And they're also not used to generate further predictions, although this is tried sometimes without question, but it's not as common as in experimental. In experimental sciences, we often generalize to similar phenomenon and can be used to generate further hypotheses as we move forward, or predictions as we move forward. And lastly, engaging in arguments for evidence. In historical, if we think of like the Toulmin model and structural approach to thinking about argumentation, we would assume that in historical arguments we get a larger amount, or there's a larger amount of evidence needed to craft this narrative explanation. And you also assume that you would see more qualifiers, rebuttals, those things saying, well, this works here, but not as much here, right? There needs to be more of that in historical science arguments. And experimental, smaller amounts of evidence, forget the D's there, of evidence is needed as you move forward. So a few kind of implications, I guess. There are a number of wonderful activities out there that match this very well. If you go into the Science Teacher or Science Scope, there are quite a bit that are out there. Renee Clary and James Wandersee have published, it seems like almost every single issue, an article about an activity that is more historical science related, because that's their area of interest. So there are quite a few resources out there to get started from. This is certainly nothing new. I think for science teachers, I see this distinction between experimental and historical, as fuzzy as it may be, as a heuristic in terms of thinking about what inquiry is and what I should show for inquiry in a classroom. So familiarizing themselves with methods, concepts, terminology outside of pure experimentation is I think, relevant. What I see in classrooms is going into an earth science classroom and talking about controls and variables, and then talking about Wegener and trying to shove the words prediction and variables and everything else into that framework, because that's the language we have. That's the only language we tend to have in classrooms to describe the work of scientists. And so extending that language, I think, is a paramount piece of this. For science teacher educators, to provide more authentic images and examples of historical sciences, not just the end results, but science in the making. How do they know what they know? And curriculum developers to focus not just on the end results, but also the practices of historical science. How do these look different within these? So, in conclusion, I want to take us back about 15 years to inquiry and the National Science Education Standards, which had a major impact on the way that people framed inquiry within in the United States and further. They describe scientific inquiry as the diverse ways in which scientists study the natural world and propose explanations based on the evidence derived from their work. This definition is, without question, large enough, casts a large enough net to include everything I've talked about today, just like their current framework casts a large enough net to include everything I've talked about today. And they're one example, in the very beginning of this document, they're one example of scientific inquiry. Remember they had one with kids? And then they had this one, was Brian Atwater's discovery about the great subduction zone earthquake in the northwest of 1700, which is a wonderful story. So this was in the most important framing document. This was the one example of scientific inquiry given, and I don't think that it made much of an impact. So I think we can learn from that in terms of just providing these images isn't enough. I think we need this heuristic of thinking about ways that we can categorize different types of methods, so we can make sure that we give examples of those, and also change our language to be more inclusive of terms that are helpful across this. So I think this distinction between experimental and historical sciences provides a framework from which to more fully integrate the ways in which researchers in the historical sciences construct new knowledge. It's not enough to focus on end products. The way in which the community of scientists have made those discoveries are vital and important as well, and I think lead to all these problems that we saw in the very beginning. And the distinct methodologies and patterns of reasoning and arguing employed in the historical sciences need to be included in our classroom inquiry experiences to give students a richer and more complete image of science. And with that, if you have any questions, and I'm happy to take them.
All right, thanks. Rick.
Thanks.
We have some time for questions, so Ireland?
Please.
Yes. So you classify evolutionary biology as an historical science.
Right. In which a lot of experimentation happens.
Completely.
Right.
I do not completely agree with you, and I want to know what is the definition you use for evolutionary biology to consider it a historical science.
Let me pop back here. I think, and this was on there earlier, and I don't know that I emphasized it enough. I also distinguish between the micro and the macro. So the focus here is on the micro or the macro evolutionary biology versus micro evolutionary biology, without a doubt. Did I not say it?
Yeah.
I think I had it on the slide.
Micro and macro, wasn't sure if, in my memory, wasn't sure if you were referring specifically to evolution.
Right. So I was thinking macro, in terms of macroevolution, absolutely.
Macroevolution.
And again, fuzzy boundaries, right? And the idea being that there are tons of experiments that happen in plenty of historical sciences, and there are experimental scientists who dabble in using some of these terms. Physicists abduce, right? They use abduction, they reason with analogy. So all of these are, one of the interesting things about thinking about like these, adding perhaps these four terms into our lexicon of understanding about how science works, is that they're relevant all across. Right? The physicists, chemists use multiple working hypotheses at times. It's just not as common. Some of these are more common in different types of methodologies than others.
Yeah.
That's the idea.
I don't know if this is related. We are coming following
Sure.
what you just said. I'm concerned that evolutionary biology is only considered a historical science, and that's the way it's brought to K-12.
Right.
Because
Right.
when you have religious issues, it's there where it's
Right.
going to encounter the most issues. Instead, if you also show the micro side of evolutionary biology,
Right.
which is probably more intuitive to many people,
Right.
you're going to have a better acceptance of the evolutionary theory.
Right.
And so that's just
I couldn't agree more. Yeah, without question. Yeah. Please.
So one of the things that I've encountered in K-5 experiences with science is the term observational science.
Right.
So you've got a dichotomy between experimental and historical, and observational seems useful in the sense that people can sort of see observation, like meteorology or ecology, as sort of
Right.
valid, sort of shifting them away from the only valid thing is a controlled experiment towards
Right.
like, well, we can't control everything an experiment to have, right? So that's yet another form
Yeah.
that I think might be useful. And I'm wondering, in teaching and working with K-12 teachers, what are the high leverage points that we can get across? And you're suggesting these four vocabulary words, and I'm wondering terms. I'm wondering also if the observational piece might be key, or some other aspects of, I don't know, I'm just wondering.
What's interesting is if you look at this group of philosophers who go into extreme depth, as philosophers are apt to do about these topics, what's interesting is they go back and forth, and the word historical is historical, right? It started out as looking at past events, scientists that look at past events, but over time that has been kind of pulled together even within this literature, and the definition, even though they stuck with the word historical, is broader than that. And some define it basically as non-experimental, which would be your observational. Brown, I put the citation up there but didn't talk about it. Brown wrote a really interesting paper in which he said ecology is closer to historical than experimental. Not that it's trying to understand the past, although paleoecologists do, but because of the complexity of the phenomenon they're dealing with, they have to use methods that are similar while they are experimental in nature, but they also use a lot of methodologies that are common in the historical sciences as well. So, I chose to stick with the word historical, basically to latch it with the philosophers of science who have been doing this work. But in working with kids, I think observational as a language makes more sense. But then what you lose out of it, you gain a lot out of that. But what you lose out of that is that idea about I think the experiences we give students, those that are the least present in classrooms, are really the historical ones, right? Of trying to understand past events. It's just not nearly as common as even some other observational ones, right? So the language gets confused. So my reason for the word historical is to match it to this group of people who have been doing this work. But in terms of moving forward with students, so I'm in the middle of putting together a science teacher article right now to bring this to teachers, and I keep changing it back and forth, trying to figure out the best route. And I've worked with my students on it and everything else, and there's advantages and disadvantages to both.
I wonder if you'd have more luck with the K-5 crowd, who tends to leverage the literacy pieces that consider being historical.
That's interesting. That's a very good idea. Yeah, please.
So I want to ask one question about limiting the discussion to the natural sciences. Because one example that you gave was climate change science.
Right, yes, right.
And well, when you do climate change science, you can no longer deal only with the natural world.
Right.
You begin dealing with all these socio-scientific issues that bring together human systems.
Right.
And then you have to go maybe towards system approach to study this very complex phenomenon. So I'm trying to look at the implication for teaching, and I find it limiting the discussion if you deal only with natural phenomena or with the natural world.
Right.
So I'm asking, for example, what is archaeology? Is archaeology a science or not? And there was a huge debate, actually huge divide between American archaeologists and European archaeologists in the late 1960s and 70s, when American archaeologists tried to limit archaeology only to rigorous science-based argumentation. And I find it difficult to deal with these complex phenomena if we limit our discussion only to the natural world. I would like to ask, okay, so what is the type of research that psychologists do? They do experiments. So some of the psychologists do experiments. We also do observations in what is the kind of argumentation and reasoning archaeologists use, for example, in other social or in humanities and social sciences. So I think that in order to deal more deeply with the issue of using inquiry in classrooms, we have to go beyond the traditional definitions of inquiry that refer to the natural world only.
I very much appreciate that. I do. One of the people that I cited, Peter Kosso, K-O-S-S-O, is a philosopher of science who's been really deep within all of this. But his area of expertise is archaeology. And he wrote a wonderful book kind of talking about the way in which we come to understand the past through archaeology. And he's made very strong contributions. So I'm not going to dive into whether archaeology is science or not science. I'm in no way qualified to make that judgment. But I know that the methodologies they use fit very well with the methodologies that, say, a paleontologist would use at a certain level, right? At a certain level of generalization. And the reasoning patterns that are used, all of those I think fit very well. I don't, as you move into psychology and other things, I see the point that there are some topics, a very limited amount of topics in which those do interplay. And I haven't actually put a lot of thought into that, I have to admit. But now I will. If you have more thoughts, I'd like to hear them. Yeah.
I was just thinking that those terms that you added, and this chart as well, they seem to focus on differences between disciplines rather than similarities. It's like you're sort of arguing both, and I completely understand why, but it seems to me like really those terms you're adding could be sort of collapsed into inference. And kind of back to what Christina was saying, the difference between observation and inference, and the fact that all science is inferential to different degrees and in different ways, and I wonder if that would be more helpful than, you know, using the exact terms and methodology
Right.
from every discipline.
Right. You know, so in terms of the terms, yes, those are all basic ways of inferencing, but we've had this word inferencing around for a long time, and it hasn't changed. I don't think it's changed the equation very much. So,
Teachers use it.
what's that?
I don't think teachers use it.
Right.
I don't see it anywhere.
So that's why I'm saying moving past these concepts in the language that we have into something that tries to pull it apart a bit more. And I'm wondering, does that mean people will be able to use it more? Because it won't be, we're trying to pull it apart into there are parts to this. There are lots of different types of inferences. We can make a list far more than that, right? But these are ones that seem to be the most relevant to topics that we teach in schools. And so, you know, I think the language piece is important. Why I'm focusing on the differences is because everything else focuses on the similarities. Right? So if we think about practices, we think about those, not necessarily the people that wrote it or the people in this room, but teachers think about it, okay, modeling. Modeling is this. Modeling is X, and we can use it in my science classroom. Argument is X, and we can use it in my science classroom. But trying to give them another heuristic, this other framework in their mind about, you know, actually there are these differences between them. And I don't want to go to what's the difference between molecular biology and evolutionary biology. That's too detailed. So if we can find this intermediary, and to me this level of intermediary of kind of experimental, really focusing on methodology, experimental type methodologies, and if we want to say non-experimental methodologies or historical methodologies or observational methodology, whatever term we decide to use, I think is the important part.
Yeah, I think there's too many false distinctions. That's just my
Okay.
opinion.
Right, okay.
Okay.
Yeah.
Another comment. So some of us do science by collecting data,
Right.
analyzing the data,
Right.
finding models that explain the pattern in your data. And I don't feel that that kind of science fits in either experimental nor historical. How do you call that kind of science?
I would say it's exactly both of those sciences because it's set at a level of generality. It's up here that would fit very well in both of those. I don't see an issue.
So it's a mixed type of science? It's a hybrid?
No, it's one type of methodology that I think, as a pattern of methodology, actually works very well across those.
Okay.
Right. I hope it's not, you don't feel as though I'm defining them so strongly that this is exactly what historical sciences do. That's not the goal. The goal is to give these kind of broad ideas.
That such a dichotomy exists. That's
Okay.
my point. I mean, it's like
Right.
no, all the scientists do experiments. And actually, at least in biology, a lot of us collect data.
Sure.
So that's we do, and we collect data in things that are happening right now.
Right.
I mean, that's what biomedicine does. It's
Absolutely.
population geneticists does and do. So I don't feel that it's very clear to me if we have this practice of science that's very common. It fits in either. So that's my only comment.
Okay, I appreciate the comment. To me, I think it fits very well between each of these. I think it's at a level of generalness that we collect data. Absolutely, I'm saying every single person in all of this collects data. It's the way that they collect the data. Is it through manipulating nature on a lab bench, like a physicist? Or is it going out and taking observational data in a field, or even doing a natural experiment, which is somewhere in the middle? Or is it going out and finding these traces of the past and pulling them together? Those are all collecting data. So if we look at the generality of practices, yes, we all collect data, we all base it on evidence, we all create explanations, we all use models. All of those range across everything here, to me. Yeah, please.
So one of the, some of my more recent interactions with high schoolers and college students who are thinking about this, there's a fascinating phenomena where a number of them, because of the way we've been teaching nature of science in K-12, have come to what I would almost call a fundamentalist understanding of science, right? A sort of authority of scientific method,
right.
That's absolute and unquestioned in much the way that our colleagues on the creationist side are taking the authority of one book as absolute and unquestioned. My concern, so this is in part a nice kind of way of thinking about and bringing some of the richness of the way we practice science to students. But The separating into kind of categories, methodologies within each categories also risks that phenomena within each category. Much as our physics colleagues, or several of them, would state that, well, anything that's not numeric is not science, it's not experimental, it's not science. How do we build across, these distinctions, experimental and historical, or whichever distinctions that we make, the notion that science, that inquiry into the physical phenomena that exist and our explanations of those use multiple methodologies in ways that don't leave our K-12 students and our future scientists and engineers and citizens with a notion of kind of fundamentalist methodology.
My first comment is you found students who were taught nature of science? I don't see it anywhere. I don't know where that came from. Okay, there you go, the scientific method. That's a nice point. I think that what pulls it across these is the practices. But again, kind of what I said in the beginning, the difference between micro and macro. This is all focusing on what I would consider micro level, right? What's happening on the lab bench and the computer screen out in the field. There's a whole other macro part that has been part of the consensus list, and there are multiple consensus lists about nature of science. I would contend that those haven't worked well. And so that's why I said in the beginning, I think this macro part of the way in which at a larger level these disciplines interact with each other and a host of other issues, to me needs to be well defined again, right? Or reconceptualized in a certain way. And I'm not sure exactly where to go with that, but So I think what you're asking is kind of these questions that are kind of macro-y on the macro side of thing, and most of this is really focused very micro. I don't know if that helps, but to me the practices in general, modeling, argumentation, are these things that do absolutely cut between them because they're happening in both. They're just happening in a slightly different way in both, if that makes sense. Yeah, please.
So when I think about instructional challenges here, I keep coming back to scale.
Yeah.
That when you're doing experimental sciences in the classroom, you're seeking to explain phenomena in terms of things that are smaller and happening faster than the phenomenon that you're observing. And when you're talking about the historical science, the models are things that are larger and happening slower. And that leads to real problems with the nature of data, for instance, that kids have to consider. That when you're talking historical science, most of the data is usually collected by somebody else, somewhere else, at some other time, and therefore seems a lot less immediate to them than what they can see in front of them in the classroom. And so this whole question of how do you make the array of data that's necessary to see a historical model real enough to the kids so that they can engage in that relationship between data and models. It seems to me like it's really a difficult problem.
And I think that's the exact reason it's not seen very often. So that's the next step, is to think about. So I guess partly having some different language in which to start thinking about that, partly giving teachers a reason that they can use to understand why we want to do that, why we want to spend the time at bringing, because this is about bringing in secondhand data. There's tons of problems with secondhand data, one of which is motivational, as you said, but there are a host of others. And so I don't think this distinction necessarily changes the fact that that's difficult to do in the classroom, but if it allows teachers to make it relevant and something that's worth doing in the classroom, then you push forward on it, right? Because I mean, it's a lot easier to take experimental data in the moment that the students collect, but often it's pretty problematic as well. It has its whole other host of problems, right?
We have time for about one more question, if anybody has.
Yeah, please.
I was just going to say, when you were focusing on sort of micro and the differences versus macro, which I'm assuming you're meaning are the similarities? Is that kind of how you were?
So I was kind of defining in terms of nature of science macro as being kind of the ways in which the communities function, kind of the more large scale pieces.
I was thinking that methodological naturalism, this is to me what brings them together, and what I felt like where this maybe micro distinctions were not showing that all scientists, even though they might, like you said, use the data a little differently, reflect with data a little
Right.
differently. What they're doing with and what they consider data are actually really similar.
Without question. So the way I use this with my students is the focus is on the practices. It's just in the background for the teacher, the reasons that we choose to do different practices in different ways and even tackle different types of questions, as he was stating before, is because we see that, oh, there are these different types and we should give them experiences, images of these different types. So what I wouldn't say is go in and just talk about experimental and historical sciences. Absolutely not. Talk about the practices. But then as we move through the year and move between topics, understand that this gives people a framework for thinking about the ways in which there's variety within those practices. There are differences within the way we argue. There are differences, I would imagine, in models. I don't know. There are differences in the way we plan and carry out investigations across within experimental sciences, but I'm trying to broaden it to be able to think about that in a kind of larger sense, I guess. So the focus with kids and teachers is practices, without question. But once we get to engaging in the practices, this is in the background for the teacher to think about the ways in which that can happen.
All right, let's give Ron a round of applause.
Thanks.
We have, of course, the famous Create for STEM.
Hey, thank you very much.
There's a grad student lunch. What? Where? Oh, and you want them to have the tote? That's special.
You're going to give me the bag? Woo-hoo. Yeah, that's very important.
You should deserve a round of applause for that.
Thank you.
Where is the grad student lunch?
It's at 1:30 in the Create conference room.
And just like now, or in a few minutes.
Now
If you're a grad student, head on down, free food.
Free food.
And if you're a boss, you'll get free food.